Today we're going to derive the kinematic equations. Now, here's what I would say. I think the first time I got taught this, I just was given these and they were almost like magic. And they're great because you can solve any problem with them, but I think it's really unfair to just give you magic. I think it's better for you guys to understand where they came from. Okay? So we're going to derive them real quick, and then you'll have this as video notes you can look at if you struggle at all. Now, just to set up what we're doing here, is these kinematic equations. Kinematics basically stands for motion. They only work under what? Constant acceleration. Now, the greatest example for constant acceleration for us guys, it's always easy for kids to see, is if we drop something. When we drop something, gravity is going to pull with a constant force, and we all know because of Newton's second law that F equals ma, and if mass times acceleration. And so if we drop that, it's going to accelerate at a constant amount. We all know, we've kind of reviewed it in here. What's that amount? 9.8 meters per second or 9.8 meters per second squared, right? Okay. So if I were to put a motion detector on the ceiling and I were to drop this marker, our position versus time curve would start to do this, which means that every second that goes by, you're covering more position, which means if you're covering more displacement or position every second, you have to be going faster, which means you are what? Accelerating. Okay? Now, this velocity versus time, because of the fact that it's linear, it means that every second that goes by, your speed or your velocity is getting bigger, but it's getting bigger at a constant amount, which means that you are accelerating at a constant rate. Okay? Which, if we come down to our acceleration versus time curve, that thing should be linear and be horizontal because your acceleration is staying the same all the time. Okay? And as a quick review, that we've said it enough times, but we know that the slope of the velocity of the position versus time curve yields velocity, and the slope of the velocity versus time curve yields acceleration. Calculus-wise, the derivative of this yields this. The second derivative of that yields our acceleration. Right? Okay, so we're good there. Now, let's step through this derivation. I think you guys would all agree that the average acceleration is equal to the change in velocity over change in time. Okay? Now I can rewrite that. Velocity final minus velocity initial, which is change in velocity, over time final minus time initial, which is change in time. Now, because acceleration is constant, and we have a linear velocity versus time curve, is our instantaneous velocity anywhere on here always going to be equal to the average velocity? Because it's linear, okay? So because of that, we can say that average velocity and average acceleration and instantaneous acceleration are basically equal to the same thing. Would you guys all agree? Okay? And you guys, just to review, A bar means average acceleration, A means instantaneous acceleration. Okay? So I can rewrite this, and we can write a whole bunch of things, but in physics, guys, here's what we do. We don't use V initial very often. We use something called V naught. So V naught really means V initial. Everybody cool? And V, instead of writing V final, we just write V. Okay? So this is just a little bit of nomenclature terminology. Instead of VF minus V final minus V initial, we say V minus V naught. Okay? So I rewrite this thing to say acceleration equals V minus V naught over T, just rewritten. And then we're going to manipulate this algebraically to solve for V. So we multiply by T, we get AT, and then we add V naught to both sides, and we come up with our first kinematic equation that we're going to use quite a bit is this guy right here. V equals V naught plus AT. Now, guys, the best way to get this across to you is the classic example of jumping off a cliff up at the reservoir, and kids are always like, how fast am I going when I hit the water? Well, if you have a watch, you can time how fast you're going. I'm sorry, how long it took you to hit the water. You know your acceleration is 9.8. For the sake of being up at the reservoir, you can just go with 10 because it makes the calculations a lot easier, and most of the kids aren't going to know anyways. They just think you're a smart dude. Okay? Your initial velocity is 0. So it's real simple. How fast are you going when you jump off a cliff? If you time 2 seconds, and you're averaging about 10 meters per second, you'll be going 20 meters per second. Now 20 meters per second, I don't know if you remember when we did unit conversions, roughly you double that, okay? So you'd be going about 40 miles an hour when you hit the water, a little bit less, okay? If you can tell kids that just out of your brain when you're cliff jumping, they're like, whoa, that's a smart dude, okay? All right, now, really quickly, guys, we're going to use that later over there, but we're going to keep moving down this way. Because the velocity varies linearly with time, we can express V bar as, this is kind of a big leap for some kids, average velocity is V naught plus V divided by 2. Now in our motion 1 packet, we did this a whole bunch of times, right? If we're here, and this is 0, and this goes up to 10, what was our average velocity? It was a 5, right? Well, how do you get to 5? Can you say 10 plus 0 divided by 2 is 5? Okay, so what we do is we can say our V naught plus our final velocity divided by 2 should give us our average velocity. Okay, if we progress then and say that average velocity is delta x over t, which we've established, we rewrite that as delta x equals average velocity times time, and then we plug this that we just got here in for V bar. So right there we plug that equation in. We can rewrite that thing down here as, we'll pull the 1/2 out to the front. We're going to go 1/2 V plus V naught times t. Okay? So this is our second kinematic equation that we're going to be using extensively. And this one, guys, is so easy, but kids kind of get confused. It seems hard. What is this basically doing? Well, if I take 1/2 V plus V naught, that gives me my what? Average velocity. So really what I'm taking is my average velocity times my time. If I take my average velocity times my time, shouldn't that give me the distance that I traveled? Okay. Really straightforward kinematic equation. Okay? Now, let's go here, and then we'll work our way that way. If we substitute this in for that, so right here, where we had V, which is right here, you guys see that? We're going to substitute that in for V. So we're going to get x equals 1/2 in V naught plus AT, okay, which is, let's do this. Can you guys see that variable right there? Now we've substituted that in for it. Everybody with me? Okay. And then we have plus V naught. So if we have V naught plus AT plus V naught, do we have 2 V naughts then? Okay. So we have 1/2 2 V naughts plus AT times T. If we distribute all that, which is kind of, this I probably should have done in 2 steps. What's 1/2 times 2? 1. Makes it go away. And then do I have to multiply by T as well? So I get V naught T plus 1/2 AT times T is AT squared. So this equation right here is our third kinematic equation that we're going to be using extensively. And basically what it is going to do is it's going to tell us how far we're going to travel. If we're going 50 meters per second to start with, and then we start accelerating from there, then this will help us determine how far we will travel. We'll take our initial velocity times the time that we're traveling, plus how much we're going to be accelerating times the time squared. And guys, we're going to be exploring this extensively right here. Okay, we're going to drop some things, and we're going to derive. We're going to, how do I say it? We're going to fit a curve to this, and when we fit a curve to that, it's going to come out to this exact quadratic formula, and we're going to manipulate this quite a bit. So for right now, don't worry about understanding that one at the same level you understand this one and this one. I think these two are pretty easy. This one's a little bit harder for our brains to wrap around at the beginning. Okay? And let's finish this thing off by taking this equation that we have here. I've rewritten it over here, but I've changed a few things. We have 1/2 v plus v naught, 1/2 v plus v naught. But instead of t, would you guys agree that if I rewrite this, could I rewrite it like that? If I take the v over there, and then I divide by a, could I get this? Okay, so what I'm going to do then is I'm going to take this, and I'm going to substitute it in for that t. Okay? Now, why would I do all this stuff? Well, because we're going to come up with some cool equations. Would I expect you to do this totally on your own? Not so much. That's why I'm walking you through it. Okay? If we substitute that in, we get 1/2 v plus v naught times the quantity v minus v naught all over a. Now, if we multiply those together, which is, you guys are pretty astute at mathematics, if we take v times v, we get v squared. If we take v naught times negative v naught, we get negative v naught squared. And then in the middle, you guys know FOIL. Is that a positive v naught v? And then we get a negative v naught v. What do those do to each other? Cancel each other out. So can you guys see how I got this right here? Do we call those a difference of two squares? Right? Okay. And then can you see we got the 2 on the bottom, the a on the bottom. You see how we come up with 2a on the bottom? Okay. So we get x equals this. And then, guys, we're going to simply manipulate it to solve for v squared. So we take the 2a over there. And then we take the v naught over to the other side. And we come up with v squared equals v naught squared plus 2ax for our fourth and final kinematic equation. Okay, in this one you'll notice there's no time variable. Okay, so in each one of these equations we are missing one particular variable, and that's okay because in any problem we encounter, we will look for the one equation that fits that problem the best. Okay. So here's what I would say. In conclusion, this is kind of a bunch of mathematical gymnastics. We're just substituting different things to get to different places. And I'll be honest, guys, as long as you kind of see this equation, this equation, this equation, and this equation, and your ability to use them are probably going to be the most important. But I guess what I would say is the derivation of them, I would like that to make sense to you. Okay? Not so much that you have to memorize it, but also the fact that it makes sense and it's not just magic. You can see where they came from. Okay? So we'll be spending the next couple weeks working through using these kinematic equations to solve problems.